This conference will now be recorded.
Okay, so good evening, Swastik, and welcome back to a fresh new session of market risk modeling. Today is day 7, and in the last session we were discussing so we started discussing the basics of normal distribution, right? So we said that so we had started our discussion with the basic functions, the exponential function and the logarithmic function. And then what we started doing is we started looking into the different ways in which these functions can be used to specify the key objective functions in a market risk model. So how is it that I can show so how is I can develop a exclusive moving asset price trajectory using these that and how do I regress them how is it that I can create an objective function, so how is that I can induce that element of linearity into these discussion into the asset of non-linearity and inclusiveness into an asset price dynamics using a logarithmic function and using an exponential function. How can I model an exponential or a super exponential movement using a log function? So that's what we saw. And from there, the next part that we started talking about was the more extensive application of normality, right? So more larger application of exponential behavior or exponential function in the normal distribution in the exponential functions, right? So this is so basically what we have started talking about is that so we started talking about the exponential functions and so we started talking about how an exponential function can be used to create a normal distribution. So what role does it play? How does it create this function of a normal distribution? The PDF or the probability density function of the normal distribution. How does it induce the symmetricity? And the next question that comes out is that I have talked now. Why is it that I need to understand the exponential function in market risk? Because I will be using it to so because the exponential functions can be used to uh, to characterize the PDF normal distribution. Now the question comes in is why do I need to know normal distribution? What is what is the contribution of normal distribution in this exercise? Why is it important for me to understand the assumption of normal distribution? Why is it important for me to know what a normal distribution does, right? Because normal distribution plays a very critical role in defining. So it plays a very critical role in defining the uh, the two most well documented concepts of stochasticity. So it actually helps in bringing in stochasticity or uncertainty into the models. And the two most important applications of normal distribution is number one. So one of the most important application where or one of the most important specification which uses the specification of normal distribution is the the white noise error term, right? Or the white noise. So that is a very important specification of uh, of predictive modeling. So if I am to develop any predictive model, if I am to want to model volatility, I want to do a time series forecast, I want to predict bar, whatever I want to do, that is the part which will obviously have a very critical role to play. So that concept of bar or that concept of that white noise error term, the concept of that concept of white noise will play a very critical role. That white noise tells us or that white noise captures us those uncertainties, those randomness in the system which a model cannot predict. And obviously we would want that randomness to or that specification of the randomness to be there in the model so that we can actually predict or we can come up and say that okay, this is so this is a model. This is the model that we have developed, and this is what the characteristic of the residuals. Or the residuals are white noise, so they are random. So this element of randomness is incorporated into the predictive modeling framework, because without which there would have been no predictive models, right? So if that random error term was not there, you would not be having any predictive model. So therefore, this concept or this part is actually a very important, or this white noise is a very important concept in any market risk model, because, or rather, when you are trying to frame a predictive framework of a market risk model, right? So when you are trying to develop a finance, let's say, an econometric model to predict market. So let's say I'm trying to develop a econometric model to predict the volatility, right? So I'm developing a volatility estimation model. If I'm trying to develop that model, then I have to bring in this element of stochasticity, this element of randomness into the system. So one very important way of modeling that randomness into an econometric model is done using normal distribution. So that random, that white noise error term is a normally distributed population. So that's a normal that follows a normal distribution with mean zero and a constant variance. Right. So this is something that we have over here. Now the next question that comes out over here is that the next question that comes out over here into this so in this part of the story is that what do we do with this white noise error term? What are the roles? What are the key areas that has affected that this white noise error term affects? And one of the most important model that we talk about over here is the random walk model. So it is the role of this error term which brings in that element of random walk into presence. In the last session we had seen how the simulations work, right? So with the incorporation of the random term, your model prediction just goes haywire. So it is that particular part which plays a role. So in a nutshell, one of the most important contributions that the normal distribution has, and thereby the exponential function has, is in terms of specifying the white noise error term, right? So the white noise error term is a normally distributed variable with mean zero and a constant variance. So this is a very central part into your model development or into any market risk, or any, for the matter, for any econometric exercise or any econometric modeling exercise, right? So that is something that we have. Now the next question that comes out over here is that how do we define this, right? So we have seen some basic simulations, but we also need to understand how to mathematically do this, and what are the areas that it affects, how does it enter into a model, and its entrance into a model, what are the differences that it creates, right? So what are the differences that comes up into the model? So why is it so important in a predictive modeling framework? So that's the part that we need to focus on, right? So this is one very important contribution of normal distribution, or one area where normal distribution is used to describe the stochasticity. The second part that we have over here is to the second element that we talk about, and that's very central to quantitative finance. That's the Wiener process. So the Wiener process finds extensive application in any of these quantitative finance models, including the Black-Scholes model for option pricing, right? So you actually have, so on the quantitative side, you would see that more of these pricing models would have their way. It helps in including the stochasticity into the pricing models, whereas the white noise error term is more responsible for helping in creating this issue of, or this or its role is more important in terms of a econometric model, right? So these are the two most important components that we need to understand before we move forward, and these are two very central contributions of this normal distribution. Now, one another very important part of the random of this white noise error term is to specify the random walk model, and the key contribution of random walk model is to explain or is to form a basis for explaining the concepts of stationarity, without which a time series model cannot be developed. So this, so the contribution of these functions is this basic and is this fundamental. So therefore, we need to explain, we need to understand the role of these two functions, and thereby this will be the founding basis for the econometric models on one side and on the quantitative finance framework on the other. So that's the next part of the discussion that we have. We have already seen some of the basic simulations. Today we'll focus more on the mathematical formulations. Okay, so let's try to uh, move on, like move on around that part. So the next part is, so the normal distribution is used to specify some important, there were some important concepts of stochasticity. Two important concepts of stochasticity of stochasticity are, okay, so there are these two important concepts, right? Okay, the normal distribution is, okay, the two important concepts of stochasticity, which are A, okay, the white noise error term. The white noise error term. This, the next part is the Wiener process. Now the question is that, why do you think is, so the question that comes out over here is that, why do you think is that normal distribution is so important for specifying stochasticity? I could have done it using any other, any other function. So So I could have done it using any other functions. Why is it that normal distribution is so important in specifying these stochasticity? So any thoughts on that? You can put your answer in the chat box first, then we can take it up. Okay, so one of the reasons as to why this is done is that if you think about a random process, so even if it's a Wiener process or if you even if it's a white noise error term, so you are talking about a so for an element or for distribution to generate these figures, right? So you have to so for randomness you need to have an element of symmetricity first of all. Because if it is skewed or anything, then it's not random. So you have to have a symmetric distribution for a random, for a variable to be randomly distributed, right? So therefore, that symmetricity is available in the normal distribution or in the Gaussian distribution. So that's one very important point. The second point that we have over here is that a normal distribution is an identically independently distributed distribution, right? So it has so there are identically independent, so it's an IID. So you have the identically independently distributed realizations. So all the elements over there are what? So they are like you have so what you are getting to see over here is the following. You get to see that all the outcomes are identical, they are independent, and yet they are very symmetric and they don't have any pattern. So only when these three characteristics are satisfied, then only you can model a random term. And this is only possible if you model it as a normal distribution. And therefore, any kind of randomness that you try to see being defined in your model results as or the result of it is that uh, I mean, so most of the randomness is defined using normal distribution because we know that if a normal distribution is used with appropriate assumptions of the parameters, then a symmetric, identically independently distributed set of outcomes can be generated, and thus a white noise error term or a Wiener process is best defined using a normal distribution, right? Okay. So over here in this term, so first let me define a white noise error term. Then I'll go to talk about the Wiener process. A white noise error term. A variable, say epsilon t. Okay, so a variable et is said to be a white noise error term term if it satisfies the following criteria. If it satisfies the following criteria, the variable is symmetric and does not have a definite pattern of evolution. The next is the values of the variable are identically and independently distributed. And finally, the positive and the negative values should cancel out. The negative values should cancel out such that no predominant directionality can be observed, can be. So these are the three important categories that so basically that must be there in the data, right? So these are the key characteristics, the three important characteristics that any white noise must have. So there must not be any definite pattern of evolution, and that is possible only when the distribution is symmetric. The values of the variables should be identical, independently distributed. Why? Because if the outcome is identically independently distributed, it would imply that realization of one outcome does not explain the other, and that is a very important criteria for a normal distribution. The values of this is identically independently distributed. So this characteristic ensures that one particular occurrence will not impact the next outcome or the occurrence. Next outcome or the occurrence of the variable. So these are the first thing is you should be symmetric, right? So there must not be a skewness. So if there is a skewness, you will capture that okay, this is not absolutely normal. So there is some pattern or there is some unusual concentration, right? The next thing is that the variables of the are identically independently distributed. So this means that the occurrence of one outcome will have no impact on the other. So if you are actually trying to find out the probability of A given B, you get the probability A into probability B, right? Now these two together will ensure that there is no correlation between the two error terms. So the occurrence of one is independent of the other, right? So therefore, okay, the positive and the negative value should cancel out such that no predominant directionality or impact is observed on the variable. So everything just cancels out. So if all the three together comes in, then you have a white noise error. So you cannot predict that. So there is some occurrence, there is a positive occurrence, negative occurrence cancelling out, and the probability and the chances of a negative occurring does not have any implication on the next outcome being negative as well. So we see that that doesn't really work. So If you have these three together into, so if you have these three together, then what you have is you have the, so then what you have is uh, a random term, or that's where you get to see a random outcome, right? So that's one. So if I am to talk about, so this is how a randomness would act, or a random variable, or variable which has random output generators should, or anything which generates random outcome should come up. Now that's one part. The second part of the story is that, so if I have to do this, I have to define it as a mathematical distribution. Now all these characteristics can be captured using a normal distribution. Okay. So the white noise error term is defined so the white noise error term is defined using a normal distribution with mu equal to 0 and sigma equals to constant. And sigma equals to, right. So we have these two variables. So one of them is the white noise is defined using a normal distribution with mean equal to 0 and sigma equal to constant. But using a normal distribution with mean 0 and a constant sigma. So this finally, so therefore it comes out that it has the following. So ET follows a normal distribution with mean 0 and a constant variance of sigma sigma epsilon square. Right, so I have mu equal to sigma and mu equal to 0 and sigma equal to constant, and this is how a white noise is defined. Right. Now, if this is the way I have defined the white noise, so how does the white noise look like? So we had seen the simulation in the last class. So let's just, so what I'll do is we'll very quickly recapitulate that once and then we will move. So this is how we had seen. So basically what we are trying to do is we were trying to model the random walk process, right? And the error component was random. So Just have a look into this random component. So how have I derived the randomness? So I had derived it using a normal inverse value. So through a normal distribution, the the numbers that was being generated were random numbers, and what I have done is I have done it with a mean 0 and a fixed standard deviation of 5, right? So that's the output that you have got over here, and it's very easy to see. You can see that there is no specific pattern, right? So this does not have any specific pattern, and given that it does not have any kind of a, or it does not have any specific patterns, therefore, so one of the important question that typically comes out is that, so yes, so it does not have any pattern, right? So you just have it everything around 0. It's just moving, it's just whizzing up and down, and you cannot see any definite pattern to this case either. So when I plot that, so when I do that scatter plot of this yt and yt minus 1 in the random walk, right, we get to see a similar behavior. So there is no pattern to this. So these kind of white noises are absolutely, so they focus on random features, random movements, and just one outcome does not is not affecting another outcome. So this is how a typical white noise process would look like, right? So previously there was just a bounce and it was falling down. Now you can see that it is just coming down at a negative trend. So the predictions based on that cannot be trusted, right? So therefore we'll have some important observations around this white noise random term. We'll talk about the random walk component, the random walk term, and we show that it is just the reliability, lack of reliability of that measure as an outcome. So as a data generating process, it does not have much of a reliability because everything is driven by the white noise, right? And therefore this, so if I do, if I generate 10 data points every time and take the mean, I'll see the mean is varying, you know the mean is varying because, and is varying very voraciously, because what we get to see is that there is the tendencies of the data change every time to time because it's highly random, and if it's highly random, the mean will also be highly random. There will be no patterns generated in the mean value. So that is the reason. So this is the reason as to why a normal distribution is used to specify a stochastic component, right? Okay. So a very strong example, so a very strong example of the white noise error term is seen while we specify the random walk process. Specify the random walk hypothesis, as we call it, the RWH. Right. So the data generating process for the random walk hypothesis, for the random walk model, is strongly driven by the white noise error term, thereby making that, thereby thereby making this Okay, so thereby making this okay, thereby making this so strongly driven by the white noise error term, thereby making the model outcomes very random in nature. Right. So let's try to look into the data generating process which the white noise error term generates. So we have already seen the simulation. We'll just try to reinstate it mathematically. So the random walk process is defined as so let's say y is a variable. So this yt is dependent on the historical values of yt. So y in the period t minus 1 plus et. So yt equals to yt minus 1 plus et. So it says that the realization of y is defined as this. So where it is where et follows where et follows where et follows a normal distribution with mean 0 and sigma square. So this is the specification of the random walk process. Okay, so this is the process. Now the next question. So what does the random walk says? So the difference equation in the random walk model shows the following. In the random walk hypothesis states the following. That first the value of y the value of the variable y in this current period, the current period is dependent on its value in the last period, and the and any random disturbances which can cause fluctuations from the value of y. Okay. So which cause fluctuations from the value cause fluctuations in the values of in variable the values of the variable. Okay. So Swastik has a question over here. In our market risk, error term will be mostly used in volatility-based calculations and scenarios, not in calculations, Swastik. So when you are calculating the volatility, you are calculating the volatility as on that period or as on a given time. So you are not doing that, right? So okay. So the first the value. So sorry, as I was saying, right? That in market risk, so when I'm talking about market risk and calculations, so calculations are done basis the historical period, right? So and you are doing it for a given month, right? Error term will come into place when you are predicting any market risk. If you are predicting a volatility, so you have a historical series of volatility and you are predicting the future volatility, the forward looking volatility. That is where you will require an error term. So over here, you are kind of recursively solving for this. You are saying that okay, yt is yt minus 1 plus some error term. So basically, if you see, this is nothing but an auto-regressive process. This is an AR1 process of the order 1. So if this is the if this is the series, so and you want to predict yt based on yt minus 1, can you do that? So that is what the random walk process so that is what the random walk process tries to tell you, that in the presence of that error term, is it possible for me to develop a prediction for yt based on the values of yt minus 1. So whenever you incorporate this random component into the data whenever you want to predict it whenever you want to do a forward looking prediction, not when you are looking into the not when you are calculating, right? So whenever it is predictive in nature, that's where this error term comes in, and this is why the existence of this error term is very so it is absolutely central to this predictive framework. So any econometric model that you develop, this error term is there, and is this error term which causes the difference between the actual and the predicted, because it captures those those random uncertainties which can occur, which is not there at the time of prediction but can occur at the time of realization. So that's where the actual and the observed gets differentiated. There is always a third factor which is happening. So let's say you work 8 hours every day, single day, 2 separate days. The number of lines that you code is not the same. Right. So one day you may have coded 300 lines, the other day you may have coded 295 lines. So they'll always be around a long run average, but they will not exactly be the same. This this digression because of some unknown one-time unnatural, some random natural factors. So that's precisely what the idea is. Clear, Swastik? Perfect. Okay. Okay. So basically, as I was saying, with the data generating process for the white noise error, for the random walk height, a hypothesis is as follows. So basically, what I'm trying to do is I'm trying to identify the data generating process through a recursive through a iterative process. Can be shown using an iterative process. Okay. So let y 0. That is y at time 0 be equal to y. Or let me write it like this. So y0, this is okay. So let y0 is equal to y0. So this is the y at time 0 being specified as y0. Be the initial condition of the random walk process. The initial condition of the random walk process. Be the initial condition of the random walk process. So now when we say this, so to solve any process or to identify the data generation process of any difference equation, so one of the important things that we always need to look into is the initial, is to specify the initial condition. Maybe the, because that's the first step. Now recursively iterating the random walk process, the random walk equation we get. The first thing is y1 is equal to y0. So yt minus 1 is y0, and this is et, is e1. So this is the first thing that you do over here. So what you say is that y1 is equal to y0 plus e1. This is at time t equals to 1. So at time t equals to 1, what you get to see is that your yt minus 1 is equal to y0 plus e1. So it says that y1, the y at time period 1 is explained by y0, the y at the 0th time point plus the random term at t plus 1. So similarly at time t equals to 2. So y2 is nothing but y1 plus, over here we have e2. Right. So y2 is explained by y1 plus e2. Now over here again, one thing that you can see is that y1 is nothing but, so y1 is nothing but y0 plus e2. So as you can see it over here, Over here, what I have is right. So similarly, at time 3, you will have y2 plus e2. So y2 will be nothing but e0, y0 plus e1 plus e2, like this. So it will keep on continuing, right? So therefore, what we can say is that at a time t equals to k, yk will be equal to y0 plus so this will be e, this will be ei, where ei follows normal distribution with mean 0 and variance sigma squared. E, right. So this is where I can clearly see. So what I can clearly see over here at this step is that at t equals to k, this is what the equation shows. So this is what the actual data generating process for the random walk is. So one thing you can see is that the evolution of y at any time point k, right? So at any time point k is controlled by the random term, and that is why when you incorporated the random term, you just saw your time series shifting away. You just saw how your time series kind of drifted away. So that is what, or that's how so that is how this random walk hypothesis works. So it clearly, one thing is clearly shown over here, and one thing is clearly, so one thing is very evident from here, that this series that you see over here is a very so it's a random series. This series is driven by the randomness, or the white noise error term. So the evolution, so after y0, any evolution to y1, y2, y3 is independent of the the y variables, right? It is totally driven by the white noise error term, and hence that random outcome. Now the question is, what is the importance of this random walk hypothesis? Now to assess that random walk, the characteristics of that random walk hypothesis, what we need to do is we need to assess the characteristics of this equation, of this time series equation that we have obtained, this data generating process equation that we have obtained. Now this is precisely a very, this provides a very clear basis of stationarity of the time series, right? And that is precisely what we are going to talk about next, right? So this forms the foundation of any kind of stationarity analysis in time series models, and that's where this random walk hypothesis becomes very critical, right? So let's start off with it in tomorrow's discussion. Let's not discuss this today. So let's start off with this, with the characteristics of this white noise error term, and why is it important to understand why normal distribution, why error, like why this specification, why the exponential function and the normal distribution is important, and what are the assumptions that it supports, right? So where does this find a relevance? So that's something that we going to that we can talk about in the next session. So let's start from the characteristics of this white noise process in tomorrow's discussion. We'll finish that and then we'll move on to talk about the Wiener process, whereby we'll also see how this Wiener process simulation are done, right? So these are the parts that we discuss in tomorrow's session, right? So remember, this white noise error term is going to be the crux of your uh, financial econometrics, while your Wiener process is going to be the crux of the quant finance, and both of these two would be required for prediction and management of risks for the different market products, right? So let's regroup tomorrow. Tomorrow we meet at around the same time, 4:30 p.m., and then let's take it up from there. Thanks a lot. And in the meantime, I'll try to upload all recordings and complete the drive. I could not do it because of my health issues this week. I'll do it. Thank you.